Ever wondered how medieval people built plumbing systems that lasted 800 plus years without modern tools or materials? These builders created water systems using only natural materials. Their waste management networks still outperform modern plumbing. Today, many systems across Europe are still functioning perfectly. Gravity-fed water systems medieval engineers mastered. Gravity-powered water distribution that delivered clean water to entire cities without pumps or electricity. They positioned water sources at higher elevations, then used carefully calculated pipe slopes to maintain consistent water pressure throughout distribution networks. These systems required precise elevation mapping and slope calculations that ensured adequate flow rates while preventing pipe damage from excessive pressure. The gravity-fed approach provided reliable water delivery that continued operating during power outages, floods, or mechanical failures that would disable modern pump systems. Many medieval gravity systems still supply European cities today. Clay pipe networks. Medieval craftsmen produced clay pipes that lasted centuries longer than modern plastic or metal plumbing. They used local clay, mixed with organic materials like straw or animal hair that created flexible, durable pipes resistant to cracking and corrosion. Firing techniques produced pipes with varying hardness levels suitable for different applications. Softer pipes for gentle curves, harder pipes for straight runs. Joint systems used clay collars or organic sealants that allowed thermal expansion without breaking connections. The clay composition actually improved over time as mineral deposits sealed minor imperfections, creating increasingly leak systems. These clay networks remained functional for 500 to 800 years with minimal maintenance, far exceeding modern pipe lifespans. Lead joint sealing. Medieval plumbers developed lead sealing techniques that created permanent, waterproof joints lasting centuries without failure. They heated lead to precise temperatures, then poured it into specially prepared joint spaces between clay or stone pipes. The process required understanding thermal expansion rates and cooling patterns that ensured perfect seals without cracking surrounding materials. Different lead alloys provided varying characteristics. Pure lead offered maximum flexibility, while tin lead mixtures provided harder, more durable joints. Application techniques included using wooden forms to shape molten lead, creating consistent joint profiles that distributed stress evenly across connection points. These lead-sealed joints remained leak-free for hundreds of years while maintaining flexibility that accommodated ground movement, temperature changes, and structural settling. Modern plumbing joints rarely achieve such longevity, often requiring replacement within decades due to material degradation or connection failures. Natural spring channeling. Medieval water engineers developed sophisticated spring capture systems that directed natural water sources into controlled distribution networks. Without contaminating or depleting source aquifers, they built stone or clay collection chambers around spring outlets, creating reservoirs that maintained consistent water pressure while protecting sources from surface contamination. Channeling techniques used carefully graded stone-lined channels that transported spring water over long distances without significant pressure or volume loss. Overflow systems prevented flooding during high-flow periods while ensuring adequate supply during dry seasons. Filtration chambers filled with sand, gravel, and charcoal removed impurities while maintaining natural mineral content that provided health benefits. Source protection involved constructing barriers that prevented animal contamination and surface runoff infiltration. Multiple spring integration created redundant water supplies that maintained service even if individual sources failed or became contaminated. These spring-fed systems provided cleaner water than many modern treatment plants while requiring zero energy input and minimal maintenance throughout. Centuries of continuous operation. Aqueduct construction. Medieval builders constructed aqueduct systems that transported water across vast distances using only gravity and precise engineering calculations. These elevated water channels maintained exact gradients that provided sufficient flow velocity to prevent stagnation while avoiding erosive speeds that could damage channel structures. Construction materials included stone, brick, and concrete that withstood weather exposure and structural stresses for centuries without significant deterioration. Arch construction techniques distributed weight loads efficiently while creating structures capable of spanning valleys, rivers, and uneven terrain. Channel lining used waterproof mortar and lead sheets that prevented leakage while maintaining smooth surfaces that minimized flow resistance. Bridge integration allowed aqueducts to cross obstacles without interrupting water flow or requiring complex pumping systems. Maintenance access included inspection chambers and cleaning ports that enabled regular upkeep without system shutdowns. Flow regulation used adjustable gates and overflow channels that controlled water distribution to different service areas. Many medieval aqueducts continued supplying cities for 500 to 1,000 years, delivering millions of gallons daily with reliability that modern water systems struggle to match while requiring minimal energy input and maintenance costs. Waste management systems. Medieval sanitation engineers designed comprehensive waste management systems that safely disposed of human waste while preventing contamination of water supplies and living areas. Gravity-powered sewer networks used carefully calculated slopes that maintained flow velocities sufficient to transport waste materials without creating blockages or backups. Pipe sizing calculations ensured adequate capacity for peak waste flows while preventing system overload during heavy usage periods. Separation systems kept wastewater isolated from drinking water supplies through strategic routing and elevation differences that prevented cross-contamination. Ventilation systems included vertical shafts that allowed sewer gases to escape safely while preventing dangerous gas accumulation in inhabited areas. Treatment processes used settling chambers, filtration beds, and natural decomposition that processed waste materials before final disposal. Access points provided maintenance entry while maintaining sanitary barriers that protected workers and prevented system contamination. Overflow protection included emergency spillways that diverted excess waste during flood conditions while protecting primary treatment facilities. Integration with stormwater management prevented system overload during heavy rainfall. While maintaining waste processing capabilities, these medieval sewage systems operated continuously for centuries while maintaining public health standards that exceeded many developing regions today. Processing waste without external energy while protecting communities from disease outbreaks. Water pressure regulation. Medieval hydraulic engineers developed pressure regulation systems that maintained consistent water delivery throughout distribution networks using only natural physics principles. Pressure relief systems included overflow chambers and release valves that prevented pipe damage from excessive pressure buildup while maintaining adequate service pressure for end users. Elevation compensation techniques adjusted pipe routing and chamber placement to account for topographical variations that could create pressure imbalances throughout distribution networks. Flow control mechanisms used adjustable gates, weirs, and valve systems that regulated water distribution between different service areas based on usage demands and supply availability. Distribution chamber design created pressure equalization that ensured consistent service delivery regardless of elevation differences or distance from water sources. Tank integration provided pressure stabilization through elevated storage that maintained service pressure during peak demand periods, while storing excess capacity during low usage times. Surge protection included expansion chambers and flexible connections that absorbed pressure fluctuations without damaging system components or creating service interruptions. Gradient optimization ensured pipe slopes provided adequate flow velocity, while preventing erosive pressures that could damage system infrastructure over extended operating periods. Maintenance accessibility allowed pressure system adjustments without major system shutdowns or expensive equipment replacements. These pressure regulation systems maintained consistent water service for hundreds of years while adapting to changing demand patterns and infrastructure. Modifications without requiring complex mechanical equipment or external energy sources. Filtration through sand layers. Medieval water treatment specialists created multi-layer filtration systems using natural materials that produced cleaner water than many modern treatment facilities, while requiring zero energy input or chemical additives. Sand layer construction involved carefully graded materials ranging from coarse gravel to fine sand that created progressive filtration, removing particles, bacteria, and chemical contaminants. Layer sequencing used specific particle size gradations that optimized filtration efficiency while maintaining adequate flow rates throughout the treatment process. Organic material integration included charcoal layers that absorbed chemical contaminants and odors, while beneficial bacteria layers that broke down organic pollutants naturally. Maintenance procedures involved periodic backwashing and media replacement that restored filtration capacity without requiring system shutdowns or expensive equipment. Flow rate optimization balanced treatment effectiveness with service delivery. Requirements: ensuring adequate water processing without creating supply shortages during peak demand periods, quality monitoring, used visual taste, and odor assessments that identified filtration problems before they affected water safety or system performance. Multiple stage processing included preliminary settling chambers, primary filtration layers, and final polishing systems that achieved water quality standards exceeding many modern treatment plants. Biological treatment integration utilized beneficial microorganisms that processed organic contaminants while preventing harmful bacteria growth throughout the filtration system. These natural filtration systems operated continuously for centuries while producing consistently safe, clean water that supported healthy communities without the chemical additives, energy consumption, or maintenance costs associated with modern water treatment facilities. Overflow prevention methods: medieval hydraulic. Engineers developed sophisticated overflow prevention systems that protected communities from flooding while maintaining continuous water service during extreme weather events. Stormwater management included separate drainage networks that diverted rainfall away from sewage systems. Preventing contamination and overflow conditions that could threaten public health. Channel capacity calculations ensured adequate flow handling during peak storm events while maintaining normal service levels during typical weather conditions. Spillway construction created controlled overflow paths that directed excess water away from inhabited areas while protecting critical infrastructure from flood damage. Retention systems included underground chambers and surface ponds that temporarily stored excess water during peak flow periods, releasing it gradually as system capacity became available. Integration with natural drainage utilized existing waterways and topographical features that enhanced system capacity without requiring extensive construction or modification of existing infrastructure. Emergency protocols included manual intervention procedures that allowed system operators to redirect flows, close critical valves, and implement flood protection measures during extreme events. Early warning systems used visual indicators and measurement devices that provided advance notice of potential overflow conditions, enabling preventive measures before problems became critical. Maintenance scheduling ensured overflow prevention systems remained functional through regular inspection, cleaning, and repair of critical components. Recovery procedures included rapid system restoration after flood events while maintaining service continuity during emergency conditions. These overflow prevention systems protected medieval communities from water-related disasters for centuries, while maintaining reliable service even during extreme weather events that would overwhelm many modern systems. Pipe slope calculations. Medieval engineers developed precise slope calculation methods that optimized water flow throughout plumbing networks using mathematical principles and practical engineering knowledge. Gradient determination involved careful surveying techniques that measured elevation changes across entire distribution routes while accounting for terrain variations and construction constraints. Flow velocity calculations ensured adequate water movement that prevented stagnation and contamination while avoiding erosive speeds that could damage pipe materials or create system failures. Pipe sizing coordination matched conduit diameter with slope gradients to achieve optimal flow characteristics for different water usage requirements throughout the distribution network. Construction techniques maintained precise slopes during installation using string lines, water levels, and surveying instruments that ensured consistent gradients despite challenging terrain conditions. Material considerations included pipe flexibility and joint design that accommodated ground movement while maintaining proper slopes throughout seasonal changes and long-term settling. Maintenance accessibility incorporated slope verification methods that allowed periodic checking and adjustment of gradients without major system reconstruction or service interruptions. Quality-controlled procedures included flow testing and performance monitoring that verified slope calculations achieved desired results throughout system operation. Integration challenges addressed connections between different slope sections while maintaining optimal flow characteristics throughout transitions and elevation changes. Problem-solving methods included slope modification techniques that corrected flow problems without requiring complete system reconstruction or extensive excavation. Documentation systems recorded slope specifications and performance. Data that guided future construction and maintenance activities. These slope calculation methods created plumbing systems with superior flow characteristics that operated reliably for centuries, while maintaining optimal performance without external energy inputs or complex mechanical equipment. Well and cistern. Integration medieval water system designers created comprehensive well and cistern networks that provided reliable water storage and distribution. Combining multiple water sources with sophisticated collection and management techniques, while construction involved precise excavation and lining methods that accessed groundwater while preventing contamination from surface runoff and waste infiltration. Cistern design included waterproof chambers that stored rainwater and spring water while maintaining water quality through proper covering and ventilation systems. Integration systems connected multiple water sources through distribution networks that balanced supply from different sources based on availability, quality, and seasonal variations. Pump mechanisms used manual wind-powered or water-powered systems that moved water between storage levels and distribution points. Without requiring external energy sources, overflow management included interconnected systems that directed excess water between storage facilities while preventing waste and maintaining optimal storage levels. Quality control procedures included settling chambers and filtration systems that improved water quality before storage while preventing contamination during collection and distribution processes. Maintenance protocols involved regular cleaning, inspection, and repair procedures that maintained system performance. Throughout extended operating periods while preventing major failures or contamination events, distribution, prioritization, managed water allocation during shortage periods while ensuring adequate supplies for essential needs and emergency situations. Backup systems included redundant storage capacity and alternative distribution routes that maintained service even during major system failures or maintenance activities. Seasonal management adapted system operation for varying weather conditions and demand patterns, while optimizing water collection and conservation throughout different climate cycles. Emergency procedures included water rationing protocols and alternative supply activation that maintained community water security during crisis situations. These integrated well and cistern systems provided reliable water service for centuries, while adapting to changing community needs and environmental conditions without requiring expensive infrastructure upgrades or external energy sources. These medieval DIY plumbing techniques prove that our ancestors achieved remarkable water and waste management. Using natural materials and gravity-powered engineering, their methods often produced superior results, better durability, lower maintenance costs, and longer service life than modern systems, while requiring zero energy input. Subscribe for weekly building wisdom that could revolutionize your home projects today.